All right, I'm going to begin. My name is Ben Brown. I'm coming to you from Sydney this morning, and it's my pleasure to introduce Aleksander Kubica. He's going to tell us about some work on using quantum metrological bounds in quantum error correction. This is some work he did during his postdoc at between Perimeter Institute and IQC in Waterloo. So Alex, if you're ready, please go ahead.
Hello, everyone. Thank you, Ben, for this introduction. Today, I will be talking to you how to use metrological bounds to get a simple proof of the approximate Eastin-Knill theorem. And this work was done together with Rafał Dębkowicz-Dobrzański from the University of Warsaw. So let's get started. Let me motivate a bit why I am interested in quantum error correcting codes, but it's not only me who is interested in quantum error correcting codes. Quantum error correcting codes are an important theoretical tool, and they are used not only for fault-tolerant quantum computation. This concept appears in many areas of physics, and one thing which quantum error correcting codes can give us a lot of insight is quantum phases of matter. They provide toy models which exemplify a variety of phenomena we can see in 2 dimensions, in 3 dimensions. Quantum error correcting codes have been explored recently in
these CFT.
Alex, you just muted yourself.
Hello?
You went off again. You keep. Sorry, I forgot to say at the beginning, if anybody has questions, please drop them in the Q&A or raise your hand in the chat, and I'll address them either at the end or during the talk. Yeah, depending on what the questions are. We can hear you again, Alex.
Oh, okay. Sorry for that. Yeah, I don't know what happened. Okay, so I was saying that yeah, quantum error correcting codes appear in many areas of physics, and also recently people have proposed using quantum error correcting codes to improve the precision of certain quantum metrological tasks. So if we talk about fault tolerance and building a quantum computer,
share your screen as well.
I apologize. Okay, so when we want to build a quantum computer, we want to protect quantum information from errors, but at the same time, we want to be able to perform logical computation quite easily and in a fault-tolerant way. However, there is a tension because if our codes allow to correct errors, they may not necessarily allow for a simple implementation of logical gates by transversal operations, transversal unitaries. And this tension is captured by Eastin-Knill theorem, and there have been also many follow-up works which capture this difficulty. So if we have good error correction, we can protect logical information from the detrimental effect of noise on the encoded logical information. Usually, this means that it is difficult to compute on that encoded information. So last year, there have been 2 works which explored a version of Eastin-Knill theorem, and it's an approximate version of this theorem. And the approximate here refers to the fact that we were talking about approximate error correction instead of exact error correction. And in the talk, I will be focusing on the approximate version of Eastin-Knill theorem. So the main result of our work is a simple proof of the approximate version of Eastin-Knill theorem. And in our work, we followed a slightly unorthodox approach. Namely, we use methods from quantum metrology to set limitations, to find limitations on quantum error correction. So here's the outline of my talk. I will start by a very brief introduction to quantum error correction, and in particular the approximate version. And then I will elaborate a bit on Eastin-Knill theorem, the limitations which this theorem imposes. I will tell you a bit how to circumvent that theorem, and I will arrive at the approximate version of Eastin-Knill theorem. And I would like to show you the proof, but first I will have to tell you a bit about quantum metrological bounds. I will view those bounds as some tool, which and using this tool, I will be able to present a short proof of the approximate Eastin-Knill theorem. So let's get started with quantum error correction. So what is a quantum code? Very abstractly, one can think of a quantum code as a subspace of the Hilbert space. So what we have is we have some logical information, and we have some logical Hilbert space, and we want to encode it into the Hilbert space of some bigger system. So we have some encoding map, curly E. And typically we assume that our physical system consists of a few small subsystems, and the Hilbert space has a tensor product structure. And in the talk, I will assume that I have a finite number of subsystems, and the dimensionality of each local Hilbert space is finite. So when we talk about error correction, I have to tell you about a very simple yet very powerful condition, Knill-Laflamme condition. This condition tells us that there exists a recovery map R for some set of errors, and this recovery map can undo the effect of errors on the encoded information if and only if the condition on the right hand side is satisfied. So basically different errors take orthogonal states to basically orthogonal states. And I want to emphasize that this recovery map can correct errors exactly. We can get the encoded information perfectly back. And one can ask whether this approach is not ever-limiting, because we just say that the recovery exists for some set of errors. It turns out that this is actually quite broad, because if we can correct some set of errors, then we can correct any linear combination of those errors. So now let's talk a bit about approximate error correction. So it turns out that allowing for some negligible error in the recovery can lead to surprisingly good codes. So what is the setting we consider? So we have some encoding map, curly E, we have some noise, and we have some recovery operation. So for this talk, I will assume that the noise has this tensor product structure, and this is a fairly reasonable standard assumption which people take in quantum error correction. And so if we're given the noise affecting our system, what we usually can optimize is the encoding and the recovery operation. And we want to pick the encoding, we want to pick a code which can handle as much noise as possible, and we also want to be smart with choosing the recovery operator, which attempts at undoing the effects of the noise on the encoded information. So what do we want exactly? Well, so we want the following channel, the following composite channel, which consists of the encoding channel, followed by the noise, followed by the recovery. And we want that channel to be as close to the identity channel on the logical level as possible. And it should be epsilon close to the identity channel. And one can make it more precise if we use the notions of the Beer's distance for channels. And this is some distance measure which uses the worst case entanglement fidelity for two channels. So Benny and Oreshkov a couple of years ago introduced this notion of epsilon correctability. In particular, one says that the code with the encoding map curly E is epsilon correctable for some noise n if there exists a recovery operator R such that the composite channel, which is the encoding, the noise, and the recovery, and that this composite channel and the identity channel, the distance between those two channels is not greater than epsilon. So, yes, this is the key notion which will be appearing in the rest of the talk. So now I would like to tell you a bit about Eastin-Knill theorem and the limitations this theorem imposes, how to circumvent them, and also I will wrap up this section with an approximate version of the Eastin-Knill theorem. So as I said at the beginning of the talk, we want to perform a fault-tolerant quantum computation. And in particular, we don't want to spread errors in some uncontrollable way. We cannot perform any unitary in a reckless way because some complicated unitaries can spread errors throughout the system. So a notion which is very useful, it's a very simple one, but very powerful. It's a notion of a transversal gate. A transversal gate is a unitary which is a tensor product of single qubit unitaries. Single qubit unitaries can, acting on each subsystem, can be different. And we can immediately see that transversal gates do not spread errors in an uncontrollable way. And namely, if one qubit is affected by noise, and if we apply a transversal gate to the system, errors on that qubit will not spread to other errors. However, if we were to apply some unitary which is composed of multi-qubit gates, one fault affecting one qubit can potentially spread to many qubits and eventually can lead to a problem, to a logical failure. It can affect the encoded logical information. So a natural question one asks is whether there exists a fault-tolerant universal set of transversal gates. Because if such a set existed, we would be done with the problem of fault-tolerant universal computation. We would just implement logical operations using transversal gates. Unfortunately, such a gate set does not exist, and this is captured by Eastin-Knill theorem. The theorem says that transversal logical unitaries are not universal for any non-trivial error detecting quantum code. So let me make now a digression about quantifying Eastin-Knill theorem. Eastin-Knill theorem, in a form I stated, it's an existential theorem. It tells that there does not exist a code with a universal gate set consisting of transversal gates. But we don't know what is possible, what we can hope to achieve, or if there are examples of interesting codes with many transversal gates. So there have been quite a few attempts to quantify Eastin-Knill theorem. And in particular, a few years ago, there were results by Bravi and Koenig, as well as Paslavsky and Yoshida. Those works established that for the dimensional topological stabilizer or subsystem codes, if we implement unitaries via some local constant depth circuits, and then those unitaries will be in the div level of the Clifford hierarchy. So I know that this is a bit packed statement. So first, what are topological codes? Topological codes can be viewed as quantum codes with qubits, physical qubits placed on some manifold. Think of it as a surface of a torus, or it could be on a plane. And then the stabilizer operators, the checks we measure, and they are geometrically local. And with topological codes, logical information is encoded non-locally in the system. So if errors can only affect local regions, then they cannot implement logical operation easily. So to unpack the second part of the statement, I need to tell you what the Clifford hierarchy is. So Clifford hierarchy is defined recursively. And first level of the Clifford hierarchy is it consists of Pauli operators. And second level of the Clifford hierarchy consists of Clifford operations. So the J+1 level of the hierarchy is defined as the set of all the unitaries for which the group commutator of that unitary with a Pauli operator is in the Jth level of the hierarchy. So let's see that this is consistent with what I told you about, say, the second level being the Clifford group. So the Clifford group is defined as all the unitaries which take Pauli operators and map them to be Pauli operators, potentially some other Pauli operators. And this is indeed consistent with the definition. So, however, if we want to have a universal gate set, we need some gates from the third or higher level of the Clifford hierarchy. So what those results by Bravi, Koenig, and Paslavsky and Yoshida tell us is that if we want to have a non-Clifford gate, we necessarily have to go to 3 spatial dimensions. Of course, there could be some tricks one can play if we trade the third spatial dimension with time, and then we could have non-Clifford gates in 2-dimensional codes, but they would not be implemented by a constant depth unitary. They would be implemented via some process which will take some time. Okay, so last year, my collaborators, Thomas Joachim O'Connor and Ted Yoder, and I, we had a paper in which we also had a new look at how to quantify Eastin-Knill theorem, and we introduced this this new code quantity, which we called the disjointness. One can compute this quantity for any code, and then we will have a guarantee that all constant depth unitaries, not necessarily local, they can be, they don't have to be geometrically local. Those unitaries, they can consist of gates which are non-local, geometrically non-local. And if we find, so our result is that for all those unitaries, all what we can hope for is that they can implement gates from up to the nth level of the Clifford hierarchy. And this does not tell us that the gates from the nth level are possible. This tells us that we cannot hope for gates from outside the nth level. And let me just emphasize that the Clifford hierarchy is so the hierarchy is basically defined in a way that the lower level is included in the higher level. So an actual question which you may ask now is whether there exists codes which saturate the hierarchy. And it turns out that indeed there are codes like that. So for instance, if we consider the color code family in the dimensions, or even d copies of the d-dimensional toric code in the dimensions, both of those code families, they will have d-dimensional, they will have gates from the div level of the Clifford hierarchy. So in particular, if we consider three-dimensional color code, or if we consider 3 copies of the three-dimensional toric code, they will have gates which are from the 3rd level of the Clifford hierarchy. And as I told you earlier, those gates are necessary in order to achieve universal quantum computation. Okay, so this slide was a bit of a digression, but I thought it may be important to paint, to explain the context of Eastin-Knill theorem. So now one can start thinking about how to avoid Eastin-Knill theorem, and indeed there have been many works how one can circumvent that no-go theorem. So there are many possible ways. So one can loosen a notion of transversality. So one does not consider unitaries which are tensor product of single qubit unitaries. One may consider unitaries which are implemented by constant depth circuits, or one may consider a concatenation of codes and choosing how one can partition the system into subsystems. One can also employ non-unitary operations, and this approach is basically what a state distillation is about. We perform some measurements and then we do some post-selection. Also, one can avoid the no-go result by Eastin-Knill by using the code, because what Eastin-Knill theorem tells us is that there does not exist a code, a single code. However, if we consider, say, 2 codes, they can have different transversal gates, and if we can fault-tolerantly switch between those 2 codes, we'll be able to implement a universal gate set with transversal gates. However, this will not be done within 1 code. It will be done with, say, 2 codes. And indeed, it's possible, for instance, with the 3-dimensional color code. One considers the subsystem version of the color code and the stabilizer version of the color code. Also, we can avoid Eastin-Knill theorem by violating the assumption about the dimensionality of the local Hibert space. We can consider, for instance, some subsystems with infinitely dimensional local Hibert space, and this was done in the context of reference frames. And lastly, one can allow some small errors. This is the setting of approximate error correction, and indeed, I will be looking at this setting more in the rest of the talk. So, what is the setting I'd like to consider with you? So, we want to allow for the recovery to be not perfect, to be to be approximate. So we consider now approximate quantum error correction and a covariant code with transversal gates. So so what it means is the following. So we consider some logical rotations generated by some generator T. So you can think of having logical rotations along the z-axis by some arbitrary angle theta. So what we want is that if we want to implement a logical rotation, if we want to implement a rotation by some angle theta on the logical level, this can be done by implementing a unitary which is dependent on the same parameter theta on the logical level. That's what covariance tells us, that this unitary on the logical level parameterized by theta, it can be implemented on the physical level and parameterized. The unitaries will be parameterized by the same parameter theta. And what transversality tells us is that this physical unitary theta can be further split into a tensor product of unitaries which act independently on each and every subsystem. So that's the setting we want to consider. We have a covariant code with transversal gates, and we can just look at rotations along some axes. And the approximate version of the Eastin-Knill theorem can be stated as follows. So let curly E be a covariant code with transversal gates, which are those rotations generated by some generator TL. And then if the code is epsilon correctable for some noise which has the tensor product structure, and then epsilon is lower bounded by some quantity. So this quantity depends on the eigenvalue spread of the generator which generates those logical rotations, delta TL, and on some quantity f up, which I will not elaborate on right now. I will explain to you in the next slide. It's some quantity which can be evaluated, and it comes from quantum metrological considerations. So remember, epsilon parameterizes how well our code performs in correcting errors. So it tells us that the composite channel, which consists of the encoding map, the noise, and the recovery, that this composite channel is epsilon close to the identity channel on the logical level. So very roughly speaking, what the approximate Eastin-Knill theorem tell you is if you want a covariant code with transversal gates, then there is some price one pays, namely the performance of the code cannot be ideal. There is some bound that the quality of the code is bounded, and so let me copy the statement of the theorem. I didn't do anything here. It's just the same theorems copy. So let's look closer at it now. So first, this quantity f up is quite easy to find for many relevant noise models. So for instance, for the independent erasure or the independent depolarizing noise, one can straightforwardly find it, and this quantity f up will be in those cases of the erasure or the depolarizing noise will be sum of the eigenvalue spread for the local generators square times some function of the noise, and in case of the erasure or depolarizing noise of strength P, it's gonna be a quite simple function. So what is important is basically f up scales linearly with the number of subsystems we have. Also, I would like to make a comment that this assumption about code being covariant is actually weaker than having a universal gate set. And the way you should think of it is that what is stated in the theorem is basically that we have rotations along the z-axis, say, but what having a universal gate set, what it would mean that we could rotate along the x, y, and z axis. So clearly, if we have universality, we would have, say, this U1 covariance, to be more precise. Also, we can have a version of the approximate Eastin-Knill theorem in a scenario that in which we have a code which encodes one logical qubit into n qubits. And if we assume that this code has a universal gate set of transversal gates, then there is some lower bound on epsilon on this correctability parameter. And in this bound, the dimensionality of the local Hilbert space shows up. But the expression is very similar to the one I showed you earlier. Okay, so that is the statement of the approximate Eastin-Knill theorem. So we want to prove it, but before I can show you the proof, I need to tell you about some tools we're going to use, namely quantum metrological bounds. So what is quantum metrology? Well, it's a very interesting field. But what we need to know to be able to get the proof of approximate Eastin-Knill theorem is that we need to know a bit about the channel estimation problem. So what's the setting of this problem? So we have some state, some initial state psi, and then there is some channel which depends on the parameter phi. We send the state through the channel, and then we perform some measurement. And what we want to do is we want to come up with some unbiased estimator for this parameter phi. And what we can do here is we can optimize the initial state psi, and we can also optimize the measurements. And what we would like to do is we would like to minimize the variance of this unbiased estimator. So what turns out to be very useful for this channel estimation problem is the notion of quantum Fisher information. And quantum Fisher information is useful for bounding the variance of this unbiased estimator via the quantum Kramer-Rao inequality. And it tells the variance of this unbiased estimator is lower bounded by 1 over f. And f here is quantum Fisher information, which can be computed for that setting. So I will not give you a precise definition of how to find quantum Fisher information. However, I'll show it to you how to compute quantum Fisher information for pure states. Yes, so if our parameter yes, if this is the quantum Fisher information for pure states. And what is interesting is to analyze the case in which our state is undergoes some unitary evolution due to some Hamiltonian acting on it. So if we plug this state into the formula above, we will get the so-called time energy uncertainty relation. So we will see that the variance of estimating the time is lower bounded by 1 over the variance of the energy in the system. Okay, so now let me tell you a bit about metrological bounds. So now we consider a problem. We want to estimate some parameter, and we can use our channel n times. So for instance, imagine we have some rotation along z-axis, and our parameter phi tells us, the angle of rotation. So we want to know how precisely we can estimate phi. So this question boils down to understanding how quantum information can scale if we have n uses of the channel. And it turns out that we consider an uncorrelated scheme, and namely we use the channel n times, but the uses are uncorrelated. quantum feature information can scale linearly with the number of uses. However, if we use some entanglement enhanced scheme, the quantum feature information can scale quadratically. And if it scales quadratically, we talk about the so-called Heisenberg scaling limit. It turns out that it doesn't really matter if we use the channel in parallel or if we have some sequential procedure. All what matters is that the total number of the parameter encoding channel we used is n. So let me now depict the most general metrological protocol. It would consist of state preparation. Then we would have some parameter encoding channels, u theta, acting on subsystems A1 through AN. Then there could be some noise affecting each subsystem. Then we could have some control, which acts on our system A and also on some ancillas. And then we have more parameter encoding channels, u subscript theta, and more noise, more control, and then we perform some arbitrary measurement at the end. So we know from those quantum metrological bounds that the quantum feature information in that setting can scale at most quadratically in the number of channel uses. So what we need to do now is we need to write down a cross representation of the parameter encoding channel, which consists of basically the unitary, which depends on the parameter we want to estimate theta, and followed by noise acting on each of the subsystems. So we write that parameter encoding channel in terms of cross operators. There are many ways to write it. And it can happen that in the presence of noise, quantum feature information can scale only linearly with the number of channel uses. And this can happen if this quantity beta, it gets a bit technical, but you know, if certain conditions are satisfied, and they can be checked. If certain conditions are satisfied, then the quantum feature information will scale linearly with the number of channel uses. And this is where those quantum metrological bounds become quite powerful, and they will allow us to prove Eastin-Knill theorem in this linear scaling regime. Okay, so this was quite a technical slide, but now hopefully it's gonna be easier, and we're getting to the proof of the theorem. So here I copied again the statement of the theorem. So the last technical thing is we needed some technical lemma. So the statement of the lemma is specified on the slide, but roughly speaking, what the lemma tells us is that we have some channel, some parameter encoding channel C theta, and what we can do is we can relate quantum Fisher information for that channel with the Beer's distance between this channel and the unitary channel, the rotation by angle theta. So that's the technical lemma, and the proof idea, which I will illustrate on one slide, is as follows. We will use quantum metrological bounds, which tell us how precisely we can estimate some parameter. We will use the bounds to limit the quality of quantum error correction. So, so the big picture is we cannot perform quantum error correction too well, because if we did perform quantum error correction very well, we would be able to estimate certain parameters too well. And we know that this would violate a certain quantum metrological bounds. Okay, so that's the big picture. So here's the proof. So what we know from quantum metrological bounds is that if we have the most generic setting of parameter estimation, if certain condition is satisfied, then the scaling of Fisher information would be linear in the number of channel uses. So we get the bound like the one stated on the right hand side. But this bound is applicable to any setting. So in particular, if we consider a protocol based on the encoding map E for our code and the recovery R, we would also not violate the quantum metrological bound in that case. So we can optimize over the input state and the parameter theta. So now what we use is we use the assumption that the code is covariant and it has transversal gates. So what we can do is we can push the unitaries from the physical level to be a unitary on the logical level. So basically, middle panel and the bubble panel are equivalent, are the same. It's just that the unitary is pushed from the physical level to the logical level. And now what we can do is we can analyze the logical channel, and we can apply the technical lemma to the logical channel. So remember, the technical lemma relates the Fisher information to the Beer's distance of certain parameter encoding channel. In our case, this parameter encoding channel is the unitary rotation followed by encoding, noise, and recovery. We should be close to the identity channel on the logical level. Okay, so, and then we throw a bunch of other assumptions. So basically, the fact that our code is epsilon correctable for the specified noise. We use contractivity and unitary invariance of the Beer's distance and some triangle inequality, and we can get that inequality. And so basically what we see is that 1 minus 8 m squared epsilon squared times m delta t squared is smaller than m times f up. So notice that there is this freedom of choosing what m is. So in particular, we will get the tightest bound on epsilon if we set m to be this quantity. And that is how we get the bound in the top right corner, which is the bound in the approximate Eastin-Knill theorem. Okay, so this was the one slide proof of the approximate Eastin-Knill theorem. So now let me make a couple of comments on the approximate Eastin-Knill theorem. So our work compared with previous work by Feist et al, as well as with and Alhambra, we have a fairly simple proof. We managed to recover a similar scaling, 1 over n, where n is number of subsystems, but our methods are applicable also beyond the erasure noise. And so in particular, we can consider very easily the depolarizing channel and so on and so forth. Whenever we can find certain Krauss representations satisfying some conditions. Also, I would like to make a comment that from the approximate Eastin-Knill theorem, one can recover the standard version of Eastin-Knill theorem. So this one can be stated in the following way, that there does not exist a finite dimensional SUDL covariant code with transversal gates and distance greater than 1. And the proof of that corollary is one-liner. It's a proof by contradiction. So take, for instance, the erasure noise and consider this erasure noise for sufficiently small noise strength P. Then we will know that the epsilon parameter, the one which captures how well our code performs, in that setting would scale as P to the D, because we can correct we can correct any errors as long as they affect at most D subsystems. So epsilon would scale as D-1 subsystem, so epsilon would scale as P to the D. However, from the metrological bound, we would know that this quantity delta t squared over something like 3√6 f up, that thing would scale as P. So if we choose P sufficiently small, we would see that epsilon is smaller than delta t squared over 3√6f, and this contradicts our theorem. So so indeed we got the standard Eastin-Knill theorem. Also, I would like to make a remark that our proof breaks down if quantum feature information grows faster than linearly, and this is all good. Our proof better breaks down in that case, because there exists the 3D qubit repetition code, and this code corrects any bit flip error, but at the same time has logical zero rotations implemented in a transversal way. So this brings me to the summary of my talk. So in my talk, I was telling about tension between doing error correction and performing a fault-tolerant computation. If we can correct an error which affects any subsystem, then we cannot really do, we cannot have a universal gate set of transversal gates. This is captured by the no-go result of Eastin-Knill. And in the talk, what I focus on is the setting where we try to circumvent Eastin-Knill theorem, and we allow for approximate error correction instead of exact error correction. But in that setting, we also end up with some no-go result, or rather, if we want to have covariant code with a transversal gates, there's a certain price we have to pay, and the code quality cannot be arbitrarily good. The code can't be arbitrarily good. There will be some lower bound on the epsilon parameter, and using the metrological approach, we can quite straightforwardly find what this lower bound is for most of considered noise models. For instance, the depolarizing noise model or the erasure noise model. And in our work, we presented a novel approach in which we used quantum metrological bounds to tell us something about the quality of quantum error correction. And yes, with that, I would like to thank you for your attention. And this is the archive number to the paper. Thank you.
All right. Thank you for your talk, Alex. Let's show our appreciation with, I don't know, the clapping emojis and things in the chat. I can clap, just one person clapping. Yeah, that was Alex Kubica telling us about his work on quantum metrology and how it links with quantum error correction. We're 10 minutes from the end, so we have plenty of time for questions. Do we have any questions? Well, maybe I can begin with the obvious one. What assumptions have you made, Alex? And what ones can we try and neglect to get around this?
So let's see. So the statement of the theorem is as follows. So we have some code which has transversal gates, and then we know how well this code can perform. So so that is the setting, right?
Mm-hmm. Okay. Yeah.
So what we need in order to get explicit bounds is, for instance, the structure of the noise, and that it affects each subsystem independently. Of course, if your subsystems, maybe, you know, if there are pairs of subsystems which are affected together, you can lump them together and call, you know, those pairs to be your, you know, coarse grained subsystem. But an interesting case is where the noise becomes more correlated. Then our approach could still work in principle. There is nothing, it doesn't break down immediately. And the problem is whether we can find explicitly this lower bound f up, because this f up can be found very easily if your noise is IID. But if it's, you know, correlated, then it's kind of, you know, an open question how to do it explicitly, how to find it explicitly.
Yeah, it's tricky. Hey, noise and metrology, they're kind of the same thing. You're measuring noise in a way. Let's see. So do we have any more questions? What do we have here? Forgive me if I mispronounced your name, but Sang-Hwan Song says, how do you expect about achievability or the upper bound of epsilon? Do you expect it to be close to 1?
Sorry, could you repeat it?
How do you expect the achievability? Do you expect to be able to achieve the upper bound of epsilon?
Yeah.
And do you expect it to be close to 1? I'm also going to unmute.
Yeah, the achievability of this bound. So in our work, we didn't explore codes which kind of can saturate the bound, but in the original papers by Feist et al. And Woods and Alhambra, they do consider codes which somehow get close to those bounds. And similarly, there was a work by Sisi Zhu, Liang Zhang, and Ziwen Liu, a month after our paper appeared on the archive, and they use also metrological things in order to get similar proof of the approximate Eastin-Knill theorem, and they did provide codes which got close to the bound. So the bound can be saturated basically.
Okay. So like we still have 5 minutes for questions, so we have a couple more here. So Shenji is asking, roughly speaking, is the lower bound epsilon determined by the Heisenberg uncertainty relation? I'm going to hit the allow to talk button, Shenji, if you want to follow up. Alex's answer. Yeah, is the lower bound epsilon determined by the Heisenberg uncertainty relation?
So right, so with this Heisenberg uncertainty relation, I think those are similar concepts, but not quite. So it's more like the way I view, say, you know, there is this what I said to you early on in the talk is that there is this time energy uncertainty relation which appears, and this can be recovered basically from this question of parameter estimation using this Kramer-Rao inequality. It tells us basically that the variance of, you know, say a time is lower bounded by 1 over the variance of the energy. So that's how this kind of appears here. And when it comes to the approximate Eastin-Knill theorem, the way I view it is basically quantum error correction cannot perform too well, because if it performed too good, if it performed too well, then we would be able to estimate certain parameters. We would be able to perform those quantum metrological tasks too well, and that would violate certain quantum metrological bounds.
Okay. I let you talk, Shinji. If you could speak up fast if you want to follow up on that. Otherwise, he's got it. Okay. And then Mitsuki Katsuda asks what types of noise are considered in this research. I'll also unmute you if you want to follow up.
So yes, so in this in our work, we can basically handle any noise model, because so this reasoning works as long as we can get linear scaling of quantum Fisher information. However, in order to explicitly find Krauss representation of your parameter encoding channel, we can do it for certain noise models like the depolarizing noise model or the erasure noise model. So, but yes, so our reasoning is not limited to the to noise models like the erasure or the polarizing noise model, but for those noise models, we can explicitly tell you that this is the bound. So that's what we should think of what we did in our paper.
The amplitude damping noise or phase damping or rotation error are they correct applicable?
Sorry, I will.
Oh, Alex has gone mute again. Are you there?
Am I on? Can you hear me?
Yeah, we can hear you again.
All right, sorry. Yeah, so I see the next question about constant factors. So, so to us, or at least I was mostly interested in getting a simple proof of approximate Eastin-Knill theorem, which kind of fits on one slide, given you explained some things, before, but we didn't care too much with optimizing the constants in the inequality, or also we were a bit sloppy in our proof, in a sense. We used steps which were not necessarily super tight, like the triangle inequality at some point. So if you were to find the most tight version of the inequality, I'm sure the one we provide is not the tightest, so you could optimize it.
Thank you very much.
Right. Yeah, thank you, Alex. We're right on 12 o'clock now, which is just the right time to stop. Let's thank Alex again in the chat or with the clap, or any which way you know how to do it on Zoom. I can clap one more time.